Hello, I'm Mr. McBrien. This is SPH3U, Motion in Two Dimensions. So what we're going to do today is take everything that we've learned from the one-dimensional case and move it into two dimensions in preparation for our final stage of kinematics. So let's consider a new problem of adding vectors. Mr. Fox walks 1.0 meters north and 2.0 meters east. What's his resulting displacement? So to start this problem, and it's my strong recommendation that you follow this with virtually any of the two-dimensional vector problems, you should draw the vector diagram. And usually you'll find it easiest to draw the longest vector first. So let's do that. We've got 2 meters east, followed by 1 meter north. And our resultant vector, the addition of these two vectors, is as shown in red. It's a trivial problem for grade 11 students to find the magnitude of this displacement. It's pretty simple. We use the Pythagorean theorem, and a squared plus b squared equals c squared, right? So c is the resultant vector, or the magnitude of the resultant vector. 1 meter squared plus 2 meters squared equals c squared. C equals the root of 5 meters squared, or 2.2 meters, rounding to two significant figures. So, a pretty easy problem. The direction is really not much more difficult. We simply have to get that direction by using trigonometry. What we don't want to do is report northeast. Northeast is a very specific direction. It means north 45 degrees east and equally east 45 degrees north. So it's the direction directly between, or halfway between, north and east, and that is not this case. So instead, we'll use trigonometry to solve the problem. Okay, so first we have to place theta for our angle, and then from there we use SOHCAHTOA to figure out which ratio to use. So since we have, in this case, we don't have the hypotenuse, we have the opposite and the adjacent, we need SOHCAHTOA tan. So tan theta equals opposite over adjacent equals 1 meter over 2 meters. And we can very quickly extract out that theta equals 27 degrees. We're not finished. We need to report this clearly, what we've got. And what we can say then is that the resultant vector, the result of adding together those two vectors, is a displacement of 2.2 meters, 27 degrees north of east. And the designation here, it would be equally appropriate to report north 90 minus 27 east. In other words, north 63 degrees east. Okay, so we can do the exact same thing with vectors that are not at 90 degrees to each other. So in this case, Ms. Roseberry walks 1.0 meters east and 1.4 meters northeast, and we want to get her resulting displacement. Now there are several ways to solve this problem, but we'll start in any case by drawing the vector diagram. By drawing the vector diagram. So here's our vector diagram here. one of the easiest ways to solve this problem is to break the angled vector 1.4 meters northeast down into horizontal and vertical components. And we'll do that here. So 1.4 meters northeast, we need to get our x and y components of this vector. By definition, it's 45 degrees is theta. Then we can use trigonometry once again to solve for x and y. So cos 45 degrees equals x over 1.4 meters. X equals 1.4 meters times cos 45. X equals 1 meter. And similarly, sine 45 degrees gives us y equals 1 meter. So now we have our vector broken into its x and y components. And what we can do from there is turn our original problem into this one, where our first vector remains the same. Our second vector was broken up into 1 meter east and 1 meter north. And so the sum of these is this. And of course, this is the mathematics of this is identical to our first problem, 2 meters east, 1 meter north. And the resultant again will be the same, 2.2 meters, 27 degrees north of east. Okay, we can do the exact same thing with regards to velocity. So Amy is walking 2 meters per second east. Brad is walking 1 meter per second south. What's Amy's velocity relative to Brad? And now we have to go back to our problem of designing our vector expression. So in this case, we can say that our velocity of Amy with respect to Brad is equivalent to the velocity of Amy with respect to the street, plus the velocity of the street with respect to Brad. Now we weren't given the street with respect to Brad. We were given Brad with respect to the street. So, of course, what we need to do when we want to reverse the direction of the vector, what do? We change the sign. So in this case, from south to north. And we get 2.0 meters per second east plus 1.0 meters per second north. And again, the mathematics is identical. In this case, though, we're just reporting velocity instead of displacement. But the mathematics of solving that problem would be identical to our first problem. So we can subtract vectors by adding the opposite vector. And that's kind of what we do here. So acceleration in 2 dimensions. A car driving at 12 meters per second north turns a corner in 3 seconds and proceeds at 12 meters per second east. What was the acceleration of the car during those 3 seconds? Okay, well, we start with our equation for acceleration. Acceleration equals v2 minus v1 over delta t. And now we're going to use our trick of adding the opposite vector. So it equals v2 plus negative v1 over delta t. And the expression becomes this. The acceleration is v2, 12 meters per second east, plus v1 in the opposite direction. 12 meters per second north becomes 12 meters per second south. And of course, delta t is 3 seconds. And we can again pretty quickly use Pythagoras and trigonometry to get the angles and the intensity. So this becomes 17 meters per second southeast divided by 3 seconds equals 5.7 meters per second squared southeast. Notice that we've divided a vector quantity by a scalar quantity. There's nothing wrong with this. We've reflected it in the units, so meters per second becomes meters per second squared, and all that the scalar affects is the intensity of the vector. Okay, so let's put some of this to practice. You can go ahead and do some of the problems from the textbook, and tomorrow we'll begin work on projectile motion. Thanks for your time.